everybody. Thanks for being here. It's I know I say this every time, but it's true every time, which is I appreciate those of you who are able to make it for the live stream. It's very helpful to me to have you there asking questions, having my back when the audio fails or whatever it is. So thanks to you when you can make it, and if you're watching the video later, that's great. Of course, also, and I hope you're having a good week. Hello, Isnam. Nice to see you. So I'm gonna jump right in. So hopefully you've seen at this point that your project one scores are back. And hello, Ember Wolf. Nice to see you. So the project, I sort of just sat there yesterday and pounded out all the grading. Hernandez, hello. So anyway, I pounded out all the grading labs and projects yesterday afternoon. So everyone who submitted something has gotten a grade back by now. And the good news is that they were really, really, really good projects overall. And in fact, my short list for demoing purposes is actually 11 different demos, which is too many, I think, probably. But I don't know. You can kind of see that I have all these tabs up here. So this is like the 11 projects that I thought just stood out for the effort. So that's probably too many to show here. I'll show 3 or 4. And so apologies to you. If I should have demoed yours for the good work, but I'm just going to randomly select from the projects that I picked to demo just to show off some of the work that you guys did. If you got a perfect score, I didn't end up sending you the scoring rubric because there's no need to fill your comments with a scoring rubric that has everything full points. So anyway, that's what that was. You just got nice comments about your work. If you were deducted any points, then I sent you the full scoring rubric on the project to show you where and why points were deducted. And that'll be in your comments associated with your grade on the assignment, which you can get in Canvas. All right, so let's quickly do some demos. And fortunately, they've kind of all come in randomly anyway. Meaning there's no particular order here. This is just the, except for, okay, let's see. There we go. So let's just run a few and see what was awesome about these or neat. So a lot of them were just very nicely done, very neat presentation like this one. It looks pretty good. Also, this person did the kind thing for the grader. Oh yeah, you are still seeing Canvas. Thank you. See, thank you, Hernandez. Okay, so here's the first demo. Thank you for seeing that and saying something. Anyway, so this was common among the really good, the well done projects, is that the displays were nicely done, and people set the stock value on at least one of the items to something low so that I could sell it out quickly, which I appreciate that because then I can immediately start trying to buy it out. Perfect. So I'll go ahead and check out, and then I'll show the full sequence here. So this person, most people did handle this part correctly, but a few people got deducted some points because they didn't handle underpayment, which it should handle. It's easy to implement, so there's no reason to not have it. And then I tended to just do this to, and then a nice receipt at the end. So that's a good one. And then I'll probably just take like the first 3 or 4 here. Okay, close that. Run this one. Yeah, so this one's cool. They have a banner at the top, which is pretty awesome. They also set some of the stock values low so that the selling out items could be handled easily. So I'll just go ahead and try to buy that out of stock. Very nice. So no, I think I will stop. So payment, I tended to do this kind of thing. Great. And then a nice clean receipt. This one looks particularly cool, just the way it's laid out on the screen. So there's the one item I bought, total paid. total owed, and then the correctly computed change at the bottom. So super, super nice one. Here's another one where the screen is nicely done and stock numbers are set low to start to not put strains on the tester. So yes, I'll continue shopping. This time I won't buy anything out. I'll just buy a couple, and then I will, let's see, did this one, okay, that one has that. So I'll check out from here just so you can see what the receipt looks like. Okay, so this one, yeah, this one has a probably a math bug in it, but I still thought that it looked kind of cool. So just showing that one off for the good looks of it. Get rid of that thing. Yeah, so this one's good. I'll just buy a thing and then I'll check out. So we can see what it looks like. I'll just pay the exact amount and we will get done. Yep, so nice clean program. Always appreciated. Just something that's very easy for me to understand what I'm supposed to do. Is very clear in its display so that I can easily... oh, I screwed this one up in the copy and paste part probably. Well, it built, so I don't know what changed. Well, I'll move on to a different one. That one built yesterday, so I don't know why that one, I can't demo it. Oh, nope, I need to recompile. All right, so this one added colors to the mix, which was quite nice. Continue, I will exit. I'll pay the total. And that one, of course, since I didn't have any change to be made, that's what I got from that one. So quite nice. One more, just at random, and then we'll move on to something else. So another one, just a clean, clear, easy to understand what I'm supposed to do. So I'll just buy, and you know, stock value set pretty low, which was very nice. This one has a cool feature, by the way. Do you notice that the cart, I can see my cart as I'm going, which I thought that was a super cool touch. And then I'll just, I'll pay $3.10 and then get my receipt. Very nice program. This person, by the way, you notice they added some logic to not print out you got 0 pennies back, so it only shows you the coinage that you're getting back. So nice ones. Those are very, very cool. All right, so let me catch up on questions. So Drew had asked, are registers used in the order they're coded or in the order that they are called? I don't know if I understand. So the book about out of order execution. I don't know that I understand the question. Registers used, so you code a procedure above the main body, right? So we're working on getting a question here. So the question, it has something to do with, are registers used in the order that they're coded? I don't understand that question. So maybe you can help me understand the question better about, are registers used in the order that they're coded? I'm sorry, I don't understand the question. Procedure 1, 2, and 3. Called 3, 2, and 1. I still don't understand. I'm sorry, I don't understand the question. Registers are used when they're used. So, yeah, I'm sorry, I don't understand the question, but maybe it'll come to me or someone in chat can help me with an answer. The registers are used when they're used, in whatever order you use them. There isn't. That's all I can think of to answer that question. But maybe we'll come up with more information where I can. Yeah. So Isnam in chat says the registers are used in the order they are referred to, and yes, the computer doesn't magically do anything. It does things when you tell it to do things. So if you use a register and then you use another register, it is in the order that you use them. So HLA, like most programming languages, and maybe this is the question, is a top to bottom system. So the order of execution in your code is from the top to the bottom, and whatever is being referenced from the top to the bottom is the thing that will be used. So anyway, maybe we'll get some clarification on that question. But nothing is going to happen that you don't cause to happen, and it will happen in the order that you cause it to happen. Let me get, there's a few week 7. Oh my gosh, I had a lot of week 7 things to demo. I'll just pick 2 at random. So there were also, let's just pick 2 week 7. So here's a couple of labs to demo. So there were a lot of good projects. So there was a small selection of the ones that had interesting features going on in them. So I tended to just test 17. So this one, there were a couple of you who figured this out, the little comma separated list. So this person actually did the logic to not insert a comma after the last value, which was a nice touch. So that was pretty cool. I'm just picking some at random. Let's do a non. So this one has nice output as well. Notice how it's all lined up real pretty on the screen. So, and I also, for whatever reason, I love the touch of thus it is not prime. I mean, that just reads super, super cool. And notice how the periods at the end of all the outputs are consistent and the spacing is good. So, dang, that was nice work. And these are just the weekly labs that these people were doing in the middle of closing out a project. So, dang, that's pretty good. This one has the extra sort of language in it. So 17 is prime and does not have factors other than 1 in itself, which is a nice touch. Let's see what this one did on 18. Okay, so I'm going to leave you with one thought. I'm going to put it in my agenda, actually. So let me close these other demos down. So one thought. From lab 7. And here's the thought. If I run a program, so here's a lab 7. What happens if I test 65535? Pretty sure that this one will break. No, they caught it. This person caught it. We should see how they did that. This person caught it. Notice this. Sweet. Good job on you. Let me undo. Go back to the last one and see if the last person caught it as well. This person, oh no, this person used signed integers to get around the problem. So, well, that's good. I guess the best labs also considered this. So go back to your lab 7 if you have time and put in 65535 and see if it causes your program to wrap around on itself. Now this program did have a mistake in it because it should not have printed out that -1, which of course would not be a factor. And somewhere in here they sort of handled that. Yeah, so they were doing as signed integers and not unsigned integers. Clever. So anyway, go back to your lab 7 if you have time and put in 65535 and see if your program wraps around on itself, which I didn't test for that because I thought that would be kind of uncool, especially in a project week. But you want to know how to handle situations like that. And I didn't talk about how you might handle it, but some of you actually did figure out ways to deal with it. So good job. Good on you that you did that. So yeah, the edge case. So this person handled it. Let me see if I can get, let me go back one more. No, that's a project. Never mind. So someone asked in chat if I can demo the edge case, and I don't know if anyone. All of these ones that I picked to demo, even though I didn't test the edge case, they seem to have handled it. There we go. There's one that didn't handle it. So it wraps around on itself and it keeps going back through and back through and back through and back through. And eventually, fortunately, or at least when it tries to come back through, the program crashes. So it got up to 65535 and then wanted to, and the problem is in this loop right here. So if number is 65535 and CX is a counter, and when you get CX reaches 65535 and you increment it, it becomes 0, which continues to be less than or equal to number, and that's a problem. So it appears that some people used signed integers so that they could make it be negative and deal with it that way. Some people just detected 65535 specifically, which was a very smart way to do it. And at some point, maybe we'll come around to this problem again and we'll look at other ways. I think we have an opportunity on the second project to talk about this problem. But anyway, on your own Lab 7, you should just try it out and see if you handled that. And if you didn't, I wouldn't spend tons of time on it, but it would be interesting Piazza edition to say, here's how I fixed the wraparound problem in show factors. Anyway. Kind of interesting. Okay, so thanks for indulging me in all of those demos, but I want to show off when people do put a lot of hard work in, and I don't have time to show everybody who did great work, but there's a random sampling of the projects and the labs, which were nicely done. So anyway, thank you for the hard work on those. It's very difficult to grade mistake-ridden submissions, and it is relatively easy to grade well done submissions. So you make my life easier when you do good work, and happier as well. Okay, so there we go. We'll move on. Project 2 is a long time from now, but you should go look at it soon and start watching for things that you can use on the second project from our labs as we go through week to week. Okay, so let's, I got back to where you're seeing the browser, I think, yeah. So let's walk through the content and then we'll switch back over to the VM and we will talk about the stack, which is the new thing this week. So notice project 2 is not due till December 11th, but you should go look at it sooner than later and consider what it is that it demands of you. And you may decide that you have the ability to begin on it today, or you may decide that you don't really have enough tools in your toolkit to bother yourself. But I would point out to you that you have 9 weeks to work on the second project. It always surprises me when I get emails on the weekend that a project's due that we've been sitting on for 2 months. So it'll happen again. It'll happen as long as anyone teaches a class like this. But officially, you have 9 weeks to work on the second project. So if you find yourself on the last weekend before December 11th looking for help and being desperate about your project, ask yourself what you did for the 8 weeks prior to that, or in fact the 9 weeks. So I'm saying that and highlighting that because today is the day to look at the second project. Today is the day, if possible, to start something that you can then build over time. You might tell yourself that you don't like to work that way. That's fine. And you may not, and you may work better with the time crunch, but hopefully some people will at least consider a different approach, which is to build the thing over time. I'm just giving you a heads up in advance that many of the things that we do in many of the labs for the next 9 weeks are designed to help you do project 2. So you want to start being on the lookout for that stuff. Okay, so week 8. So we are adding the stack to our sort of assembly toolkit. The stack is a data structure. A stack is a data structure. C++ has a stack in its standard libraries. There are a lot of programming libraries in a lot of languages that have stack data structures in them. The x86 processor and assembly language built to use the x86 processor, they have a stack built in. So you don't have to create a stack. You don't have to declare a stack. It's more or less like the registers in that it's just there. Like the registers are there. A stack is just there. And it's a data structure that you can use to store data on. And it's particularly useful for setting aside data temporarily and then making a mess of something and then restoring that data back at the end of making your mess. You'll see what I mean by that in a moment. So the stack, it's built in. It is a part of x86 assembly. You will always have the stack when you are doing x86 assembly and be able to use it for its features. And I'll talk about what a stack is and how you use it here in a bit. That's the whole thing this week, is what is the stack and how do we use it in our programs and what is it useful for. So only one section of reading from the text this week, which is about the stack and instructions that we use to interact with the stack. Homework as always. Lab I'm going to open and come back to. So discussion is a kind of a, the lab is a little bit bigger than a normal lab, but we also don't have a project due this week. So it's not a giant lab, but some of you will see that it's got a few more things to do because we are also kind of using our labs as a little bit of a review since we don't have exams. Anyway, so easy discussion this week, just a place to go say something nice and register your involvement in the class. So normal week this week, homework lab discussion, and also there is reminding you that you should go read the second project soon. You might read it and decide that you don't know what any of it is talking about, but you do know enough to create the basic structure of a program and put a little hello in there. And you may find other things that you already know how to do. Anyway, just heads up about project 2. That seems like it's very far away, but it's not as far as we might think it is. Okay, so that's the content. Let's switch views and talk about the stack in x86 assembly. So I can, actually I'll just close that. Can I make a new file? Yeah, let me make a new file. Program, okay. Interesting that it defaulted to C++. No. Okay, so I just have some code set up. I'm also going to do just a separate file to talk about the stack. So when we say a stack in computer science, oh, you're still seeing Canvas? Darn it, I thought I clicked on that. Sorry. Okay. So thank you again. Thank you, Druid. If you guys weren't here, I would have made this mistake a bunch today. For some reason, I'm just off my switch and views game. Okay, so fortunately, I hadn't gotten anything done. The only thing that I did is create the basic setup of a program. But before I do any coding work, I want to just talk about what is the stack to a computer scientist. It's a data structure, meaning it is a place where we store multiple items of data all together in one structure. An array is a data structure. A vector, if you've done C++, is a data structure. A dictionary is a data structure. If you've done Python, a map is a data structure in Go and in C++. Right? These are different algorithms that allow us to store collections of data. What's special about the stack data structure is that it is high performance, meaning it is very, very fast to put things in and take things out. And that's desirable when you're at the level of assembly. The whole point of being at the level of assembly, of course, is to make things execute efficiently. So it is a high performance data structure. And what we really mean by that is that putting data in it and getting data out are fast, super, super fast. Why is it super, super fast? First out, because it is a LIFO data structure, a last in, first out data structure. So the reason why we call it a stack is because, let me get my hands where you can see them. We call it a stack because it works like stacks do in the real world. So conceptually, that's how we program them. They are programmed to work. So when you put something in a stack, if the stack is empty, it goes basically to the bottom of the stack. And then if you add something else to the stack, it goes on top of that, right? Like a stack of books or a stack of pancakes or a stack of records on an old style record player. Stacks work that way. And then why they are so high performance is because you only ever have to place things on top. There's no searching through the stack to find the spot to put it like you would in an array. The other reason why they're high performance is because when you only remove things from the top ever. So stacks by design add new entries on the top and remove entries only from the top. And if you need a behavior in a data structure that doesn't work that way, then you don't use a stack. But it turns out that in assembly programming, the stack is very, very useful for some things. For our purposes, it will be a place where we can quickly set aside some data and then quickly restore it. So hopefully everyone understands how the stack works by stacking things on top of each other, and every new entry always goes on the top. So that is high performance. And then every retrieval of data can only retrieve the thing that's on the top. So retrieval is also very high performance. So last thing in, first thing out, last thing in, first thing out, that's LIFO. All right. And it is built in to x86 assembly. So it is just there. It is just there and waiting for you to use it. You don't have to do anything special other than write the instructions to interact with it. And there's only two instructions that we need. So the instructions are push which adds data to the top of the stack, and pop, which removes the data from the top of the stack. That's all a stack does. There is, I mean, you could, but the reason why we use the stack with push and pop is because we want the high performance that it gives. If we need to have a data structure where we are storing things and we need to be able to shuffle their order and go back sort of back and forth through the set of data to find specific things, we wouldn't use a stack. So Druid asks, how large is the assembly stack? It depends on the specific processor architecture and operating system. So the size of the stack is allocated with your sort of runtime memory for your program. And I don't know off the top of my head what the size is, but it is not unlimited, which is a good question, Druid. So when you execute a program on the x86 processor, on any processor with an operating system, the operating system will set aside memory for your program that includes space for its data and its instructions, and also this stack space. And the reason why Druid's question is important, how big is it? I don't know how precisely big it is, but it is not of unlimited size. So you can abuse the stack. We will never encounter that situation in this class, but you should note that the stack is not of infinite size. And that means that there can be occasions, although not for us, there can be occasions in the real world where stacks fill up beyond their capacity. We call that stack overflow, by the way. So that's called stack overflow, actually, when you try to push data onto a stack that is already at its capacity. Yeah, so the size of the stack is kind of operating system dependent. So we'd have to go look up the details about how much stack is set aside on an old 32-bit machine. And maybe the HLA documentation says, but I don't remember that it says. So I don't know off the top of my head precisely how big the runtime stack that we get is. But it does have a limited size. All right, so stack overflow is the thing. It's not a thing that we will experience in this class, but it is a thing where a stack can become full beyond its capacity. By the way, there's also stack underflow. Which is when you try to pop data off of an empty stack. That's called stack underflow. And those are both error conditions that if we were making heavy use of a stack data structure in some context, we would worry ourselves about. All right, so, but for us, that's unlikely to happen because we're not going to be pushing that many things. We're just going to use it as a means of preserving and restoring data in some circumstances. Okay, so there's that. So we'll add to this set then ESP. ESP is a special 32-bit register that keeps track of where the top of the stack is at any given moment. So in our class, we don't need this other than we're going to look at it today to see what the value of the stack pointer is. But there is a register in x86 called ESP, and it is the stack pointer register, and its job is to keep track of where the top of the stack is. And you can manually manipulate it, although we are not likely to do that in this class. You can move it around yourself, but we're not going to do that. We're going to use push and pop, and that will cause ESP to change. All right, so here's the tricky part about that special register, which in practical terms we don't really care about, but it's interesting how the stack works. So it's interesting, and the question is, why is it interesting? And we'll look at it today in code because it's interesting. ESP is interesting because it turns out that the stack conceptually grows, but it's upside down on the x86 processor. I'll say value. So this is an implementation detail that's beyond our scope, but ESP is interesting just when we're talking about stacks for the first time. This register that is keeping track of the top of the stack actually goes in the reverse direction of what you might think. It has no effect on the way we use the stack. It's just kind of weird because we talk about stacks as growing up as you push things on the top and then going down as you pop things off. But it turns out that in reality, the stack is implemented upside down so that when you push, the stack actually goes this way, and we'll see that with ESP, and when you pop, it goes back up. Does that affect anything about our use of the stack? It does not at all. It's just interesting. So yeah, we'll. So Druid is asking, where does the stack pointer start? So the stack pointer, so the stack is part of your program's runtime memory allocation. So where precisely in RAM your stack begins is a matter of where your operating system allocates RAM for the running instance of your program. So inside of the RAM that contains all of the contents of your running program will also be space for the stack of limited size. And where the stack begins is a matter of where the operating system placed the bank of memory for your running program in RAM. Doesn't affect us at all, but it's not going to be zero ever, because the operating system is already probably using the address space sort of at the from 0 in RAM. So the stack is going to be wherever, it's going to go with wherever the operating system sets up our running program in RAM. So its address on a not very busy system will probably often look like the same place, but on a busy system, it'll probably move around a little bit. So this is a CSCI 10 week 8 notes. Yeah, it's a detail to not get too hung up on in our class. We don't do deep diving on any of these things. The stack is not fixed in RAM. The stack is allocated with each running program, gets its own stack to work with. So if I run 2 programs, I get 2 banks of memory allocated for the 2 separate programs, and each of those banks of memory for that program also has its own stack associated with that instance of the program. So where the stack is depends on where the running program is in memory, and each separate running program gets its own stack to work with. So ESP will be a moving target of sorts. Not once your program's running, then your ESP will be wherever your running program has it. But if you shut down the program and rerun it, where your running program is living in RAM may be different, which means that your stack may start in a different place in RAM. Okay, so let's... it's okay, no problem. These are good questions, so go ahead and ask them, and I can always kind of say, let's move on if I think we should move on. But these are all relevant questions, so I'm happy to endeavor to answer them, and I'll tell you kind of when I bump up against my limits. Okay, so there's a bunch of stuff about the stack. So we're going to have one. It is built in with the space that we have available to us as we develop an application. The stack pointer, ESP, will be interesting to us today just as we explore the functioning of the push and pop instructions. So let's write some software and play around with these things. I'm going to work in hex today, which I think I hope will make it easier for you to keep track of what data is where. Okay, so where were we at? Oh yeah, so let's do some pushes and some pops and look at the stack pointer. So the first thing I'll do is I'll simply just print out the value of the stack pointer, but I'm going to work in hex because we don't really care about the data in these examples, more just understanding what's happening when I do a push and what's happening when I do a pop. Where does the data go when I do a push? Where does the data come from and go when I do a pop? And then the stack pointer is interesting because we can kind of show that on x86 the stack is weirdly upside down. It's not important, it's just interesting. So let's try it out though. So to start, let's just print the value of ESP and nothing else in the program. And let's just see where it is in RAM. What? Oh, yeah. Okay, so that is a memory location in RAM. Why it's there is because the operating system in my virtual machine, that's where it placed my running program, which means that that's where it placed the stack that goes along with my running program. In theory, if I run this program another time, so do you notice the stack moved the second time? And that's because the entire instance of the running program moved somewhere else based on the operating system's choices. So when you run a program, the operating system has to allocate a certain amount of memory to contain that program's instructions and data. And then it also allocates some space for dynamic memory purposes, it allocates the stack, which is used for a variety of things. For our purposes, we're going to directly use it. But the stack is also used at runtime for function calls and local variables for functions. That's all happening outside of our view, typically. Anyway, so you notice the stack pointer is moving, and that's because the operating system has to allocate a new set of memory for the new instance of the running program with a stack in it and run it. So yeah, there we see the program memory being moved around in RAM based on whatever choices the operating system is making, which means that the stack pointer for that running program is moving around with it. Okay, so now let's just do something. So let's move a value. I'm going to do everything in hex today so that we can easily see it, and I'm also going to have fun. 1, 2, 3, 4. I'll use the letter part. So that we can actually kind of just quickly see if the right kind of data came back. So I've put some data in a register, and then I'm going to push that register, and then use that as an opportunity to explain to you what the push does and doesn't do. So one thing that the push instruction does do is it copies that data onto the top of the stack, which means that it will also cause the ESP, the stack pointer, to move because it now has to move up some, because the top of the stack is now somewhere else. So every time you push data on the stack pointer, which is locating the top of the stack, has to move because the top of the stack moves with every new piece of data added. So a push causes the stack pointer to move. A push causes the data being pushed to be copied onto the stack. And that's important because people traditionally get confused about this. So EAX after the push. In fact, I will do EAX before the push as well. And then I will do EAX after the push. Just to prove to you that the push doesn't erase stuff. It just copies stuff. Kind of like move, except for in this case, what a push does is it copies data onto the stack. The other thing we're going to do is print the stack pointer out after the push. So let's investigate. Nope. This one. Okay, so let's investigate what just happened. So we have the stack pointer. That's wherever it is based on where the operating system loaded up our running program. And now we have EAX before the push, which is that hex value that I moved into it, copied into it. Then we have EAX after the push to point out to you that a push does not remove data from stuff. It doesn't zero things out. All it does is copy data from the target location, which is EAX, onto the top of the stack. And then what's interesting is that the stack changed. Let's do the math with the calculator and see how the stack changed. So we used to have, let me switch to hex mode. So we used to have FFC78860. So FFC78860 minus FFC7885C is 4. So at first this seems kind of weird. So the difference in the stack is that it is 4 less. Now the 4 less is because the stack is hanging upside down. You can correct me in chat, but I think that like a rock formation that's hanging from the roof is a stalactite. Hang tight, that's what I've been told, but I don't know for sure. But anyway, the x86 stack is upside down. So conceptually, the stack grows from bottom to top, except for in the x86 implementation of it, it's actually hanging upside down and growing from higher to lower. So the stack pointer actually went down by 4. And that's because when we added something to the stack, it caused the stack pointer to go down by 4 to account for what has been added to it. So here's the first sort of challenge question of the day. What does that 4 represent? Why did the stack pointer go down by 4? Does anyone know? It's a hard question. Why did it go down by 4? There you go. So it is because I pushed 4 bytes. So I pushed EAX, which is 32 bits or 4 bytes. So to accommodate those 4 bytes, the stack pointer actually shifted down those 4 bytes. That shows that 4 bytes are have now been pushed on the stack. Let's do another push. We will put let's put a beef into EBX, and then we will repeat all this, but just to remind you that pushes don't break things, they just copy. So we'll push EBX, EBX after the push, EBX, and then we will print out the stack pointer. And probably you guys know what's about to happen to the stack pointer. So what should happen to the value of the stack pointer after this second push? It changes by a certain amount somehow. That's right. So Druid, you're exactly right. So the stack pointer, because it's hanging upside down, goes down 4 more bytes, which is the amount of bytes that I pushed on there, which is 32 bits or 4 bytes. So the stack pointer should go down another 4. So we went from, notice the stack pointer changed, but 6C to 6,8. So 6C, so a C is 10, 11, 12. So C is 12. The 8 is 4 less than that. So it went down another byte. So a push actually causes the stack pointer to decrease in value, and that's because the stack is growing upside down like a stalactite. Okay, and notice also there, I pushed EBX, which has that beef value in it, and pushing doesn't change EBX. Okay, so now let's try in the other direction. So now I'm going to do a pop. Let's pop EAX first, and then we will say EAX after the pop. And then we will look at ESP. So I'll ask it again just because you guys are on the ball here. So the first question's harder. What will EAX have in it after this pop? And what will the stack pointer be after this pop? Good question, Druid. So Druid asked in chat, are you meaning to pop in this order? And I am, because I want to then sort of talk about, but you've anticipated where I'm going with this, is that I'm popping right now in a weird order, to hopefully then make the argument for why you have to be careful about the order that you do things in. So you are dead on, Druid, that there's something funny about what I'm doing. Okay, so if I pop the stack, what happens is the topmost value gets copied into EAX, but also the stack shrinks by 1. So you can think of a pop as basically removing data from the stack, because it causes the stack pointer to go down, which means that whatever was above it is effectively gone. So the pop means remove the data from the top of the stack and copy it to this location. So what should be in EAX after the pop? That's true. I was gonna, so what data in hex? And you can kind of just spell the short form of it in hex. So what's the data in hex in EAX? So you're right, Druid. It's what was formerly in EBX, which is sitting on top. But what's the word for the sort of the hex word that I spelled? Which I also thought would just kind of be funny if I got someone to type this answer in chat. Oops. Beef. Nice one, you guys. So yeah, so everyone's all right. So you're all right on top of it. So EAX will have that beef value in it, because that's what was the last thing that was pushed onto the stack. And then ESP, which direction does it go and by how much? Up by 4. So Druid is right. So when I pop, the value goes up because the stack is hanging upside down. So when I push, it goes down. When I pop, it goes up. And it should go up by the same 4 because that's how much I am popping. Okay, so let's try it. It's very interesting to experiment. All right, so here we go. So the stack pointer, of course, moved, but we can, I think, safely say at this point that after the first push, the stack has gone down by 4. The second push, the stack has gone down by another 4. So you guys were right that beef is in EAX, and then finally the stack goes back up after that first pop to where it was before the second push, as it were. So that's a lot to keep track of, but there This is why ESP is at least interesting to us, is because we can see the behavior of the stack simply by tracking where the top of the stack is at any given moment after pushes and pops. Okay, and then I'm going to go ahead and finish this thought with EBX. Okay, so now I'm going to pop the data, whatever data remains on the stack, I'm going to pop that data and store it in EBX. So when you push a value onto the stack, it doesn't matter where it came from. The stack doesn't care. So there's not like a magical EAX cell on the stack. And then I pop EAX and it goes to find where that EAX was. A pop is the top thing. It doesn't matter where it came from. It doesn't matter where it goes. Those things don't have to line up. Although Druid has already anticipated in chat that lining those things up from the programmer's perspective matters. So when I push EAX, the stack does not remember that that value came from EAX. It just has a value that's on the top. When I push EBX, the stack is not keeping track of where that value came from. That's not the EBX value. That's just a value that happened to be in EBX that's now on the top of the stack. So when I do a pop, I tell the system where I want to pop that data into, and it doesn't necessarily match where it was originally pushed from. None of that stuff matters. If I need those things to match up, I have to take care of that in code. But that's also kind of a thing that people have, traditionally think at this stage in the semester is that, well, I pushed EAX, and which means when I pop EAX, the system goes back in there and it finds that old EAX value that it stored in the stack and gets me the original EAX back. That's not how it works. Push just dumps some data on the top, and pop just pops some data off the top. Where it came from and where it's going is of no concern to the system. If it's a concern to me, the programmer, then I have to be careful about the order that I do things. Okay, so I will pop whatever's on top of the stack, this last one, storing what I popped into EBX. Doesn't matter if that's where it started, that's where it's going. And then, so what should be here, and you probably can't see it anymore, that was a long time ago. Maybe you guys can. What should EBX have in it after this final pop? Sort of the hex letters. Nice one, that one, kid. A, B, C, D. That's correct. So that original first value that we pushed, by the time we do this last pop, that was the last remaining value on the stack. So even though I pushed it, meaning I copied that value out of EAX onto the stack, when I pop it, I actually copy it back over into EBX. And it doesn't matter that it started in EAX, and it doesn't matter that it ended up in EBX. That doesn't matter. It's the order of things that I pushed and popped that really matters. So that last value will be A, B, C, D, and the stack will go up by another 4, which at this point should take the stack pointer back to where it started before I'd begun using the stack at the beginning of the program. So let's confirm that. Yep, so there's the stack at the beginning. So after the 2 pushes, it goes down. After the 2 pops, it goes back up to where it started. And then I pushed EAX first and then popped EBX and pushed EBX second. So EBX value was on top of EAX value on the stack. And then I popped them off going in the other direction. So the first pop, I put that data into EAX, which put beef into EAX, and then the last pop I targeted EBX, which took whatever was remaining on the stack, which was that ABCD, put that into EAX. By the way, this was a way of swapping the values between the two locations using the stack. So do registers have to match? Or push a lower register to the... No. Okay, so yeah, I think I get this question. No, you can push registers in any order that... So you can push the D register and then the A register and then the C register. You can push in whatever random order makes sense for your problem. And then the trick is, if you need that data to go back where it started, you have to pop in the reverse order of the way that you pushed. So no, you don't have to push A first and then B second and then C third. And maybe this is what Druid was asking earlier, but I could be wrong. So no, you can push whatever you want to, whenever you want to. Your job as the programmer is to remember what should be on top. So if I push D and then A and then B as an example, then I have to know that D's on the bottom and then A's above that and then B's above that. So that if I need the B value back in B, then the first pop needs to target B. Let's do an example so I can show you what I'm talking about. All right, so let's make a procedure and do this inside of a procedure. I don't know what to call it. I'll call it popper because that's what we're going to do with it. And I didn't want to say pusher because that sounded bad. Okay, so we can do this in procedures. So let's just say, for example, what do we want to do? Well, let's just start by let's not worry about context so much. So let's say we come into this procedure and for whatever reason we decide that we need to store the C register on the stack and we need to store the A register on the stack and we need to store the D register on the stack. So the order doesn't matter at all that I push them. Although I need to keep track of the order that I push them. All right, so now that we have those values copied onto the stack, we are free in our procedure to just wreck them. We can do weird stuff to them. That's not particularly weird, right? So I could load up some data into them. And the order that I use the registers after I've copied their original values onto the stack doesn't matter either. Okay, so I push those values on the stack. Sorry, there's a gnat in my face. And then I do whatever I want to do in my procedure with those registers. I'll just put data in them just for fun. And let's mark this up. So we're going to use the stack to preserve the values of these registers. Now in our procedure, we can just run amok on those registers all we want to, because when we get to the end of the procedure, we can use the stack to restore the register values to their original values before they were wrecked. Okay, so there's a question about doing a div, and I don't think I understand the div question in this context. So let's come back to the div question separately if there's a question about using div, because that has nothing to do with the stack. The div problem is entirely separate from the stack. But maybe your question is, Ember Wolf, is related to somehow something using the stack. So we'll try to tease out the details so that I can answer that question. But divs and the stack have nothing to do with each other directly, at least. Okay, so let's just say, for argument's sake, that our procedure popper wants to use these registers and it wants to just run amok in them and do all the stuff that it wants to do. But it also wants to make sure that the values in those registers coming in before they're wrecked are the same values going out. The registers are not stacks. So the question in chat is, if I'm using the registers as stacks, they're not stacks. The registers are registers. The stack is the stack. They're separate. You can copy values from the registers to the stack, and you can pop values from the stack back into registers. But registers are not stacks. They are registers. This is a good question, because I'm pretty sure that other people will have these same kind of thoughts to themselves. Right, so Druid asks, why would we push these onto the stack before we are overwriting them? So I'll make an example of this soon, but the idea for us will be that we can actually use the stack to not pollute the registers for other parts of our program. So for now, I'm just going to do this very direct example. So for whatever reason, and I'll show you an example where this hopefully makes more sense. So for whatever reason, when my procedure is called, I want to make sure that these registers that I want to use have the same values at the end as they did at the beginning. But they're not going to if I am overwriting them with data. Right? So I want the ability to use these registers free from guilt in this procedure, knowing that when I leave the procedure, these registers will be restored to the values they had when we got here. So I'm going to use the stack for this purpose, which is how we're going to use the stack in this class. We're going to use the stack to avoid polluting registers with bad data. So we're going to write procedures. We're going to use registers to do all kinds of different operations. And what we're going to do is make sure that, when appropriate, the registers leave the procedure the same way that they came in. So here's those register values coming in. And then I do whatever it is I'm going to do that's going to overwrite and just pollute all heck out of those registers. So, but now, because those original values are sitting on the stack, I can restore them. So the trick is, how do I restore the register values back to their original values and locations before I overwrite them? So right now, those registers are all polluted with this procedures data. How do I get them back to these values that are sitting on the stack? Yeah, that's a way to look at it, Druid. So Druid in chat says that I'm using the stack as a middleman here, and that's true. I can say, oh, you know what? A, C, and D, I'm going to set those aside, mess them up real bad, and then restore them back to the way that I found them before my procedure is done. So how do I do that? On line 20 here, how do I get the original A, C, and D values back to their original locations? So let's see, pop D. So Druid says pop D, and then pop A, and then pop C, which is correct. And then that one kid also says that you pop them. So yes, the order of pushing and popping do matter if you intend for the register values to go back to where they started, because there's no magic about that. If I need the top of the stack in A, then I pop now. If A is the second thing down, then A comes second. So the whole trick here is that if we push C, A, D, then we pop in the exact reverse order. So if the last thing pushed is D, then D is sitting on the top of the stack, which means when I pop the top of the stack to D, I am getting the original D from the top of the stack back to the register where it started. And whatever mess I made of D in the meantime now is forgotten. I pushed A second, which means it's the second thing in the stack. And so when I pop the second thing, that puts A back where it started. And then finally I pop C, which was the first thing pushed, but at this point C is now the top of the stack. So I take the value from the top of the stack, put it back where it started. So you pop, in other words, in the exact reverse order of the way that you pushed to get things back in the right order. Now, Druid made a comment or asked a question about this ordering is weird. It is a lot easier to keep track of this kind of stuff by pushing them in some kind of order. But I wanted you to know that you don't have to. But it is easier to avoid making mistakes if you push them sort of in alphabetical order, as it were, so that you can pop them in reverse alphabetical order, and you're much less likely to make a mistake, but it doesn't actually, is not a requirement. So Amber Wolf asks, so there's no way to move around in the stack. There is a way to move around in the stack by doing math on the stack pointer. It's atypical that you would ever need to do that. But technically you can add 4 or subtract 4 from the stack pointer and then use that as a locator into the stack somewhere. We won't do that because it's a can of worms, but you can actually kind of use the stack pointer to locate yourself in other areas of the stack simply by doing math on the stack pointer. But we won't do it that way. We'll just let push and pop kind of handle the stack pointer math for us and only ever deal with the top of the stack. So if we needed, we wouldn't use the stack if we had an application that needed to access data that wasn't at the top of the stack. We'd use an array or a different kind of data structure we'd create for ourselves. Okay, so this example is not super helpful, but I wanted you to see it without the confusion of what I'm about to add on top of it. So let me move this stuff. In fact, I will just kind of start a whole new program by commenting that stuff out. Okay, so let's just start a whole new program. So it's gonna be sort of artificial, but just so you can hopefully understand in context why this preserve and restore thing is at all useful. So let's just say, for argument's sake, that I'm going to say standard out.put enter a number 0 to 255. And then do a get U8. And then I will quickly move that into a different register because I'm going to repeat the same process. Okay, so at the end of this, I have the first input in BL and the second input in AL. And let's say that I have a procedure called print sum that takes two unsate values and prints their sum. So the first value is second value, print diff, first value is second value. So I'll have a print sum and a print diff. So bear with me for a moment while I build this. No variables, right? So I get an input, I copy it into BL because then I immediately get a second input which overwrites AL, right? And now I'm going to pass those two values first to print sum and then to print difference of those same two values. So print sum is simply going to do this. And then hopefully someone's screaming out, but if you don't, well, so if you see what I'm doing wrong, you're of course welcome to put it in chat what I'm doing wrong and how I might fix it. But if you don't see, then just let the error happen and then we'll figure out what to do about it. So let's print the sum. So we will move x to AL, we will add y to AL, and then we will print out x plus y equals, and then typecast that. And then we'll do something similar for print diff. I'm going to be careful about my input values so that I don't cause carries anywhere. So we'll move x to AL, we will subtract y from AL, and then we will stand it up. Let me just copy it. Minus equals. Okay, so there's my program. Let's see what happens if I run it. Save that. All right, so here's my numbers. I'm going to do numbers that work. So I'll do 10 and 3. That way 10 plus 3 is 13 and 10 minus 3 is 7. I should put new lines in there, but already I can see that there's something terribly wrong. All right, so 10, 3, oh crud. 10 plus 3 is 13, but now it says 10 minus 13 is negative 253. What happened and how do I fix it? So does anyone know in chat what happened? What did I screw up here? There's the whole program. And then here is the output that I'll squish over to the side. There's the output. So for some reason, when I did a print diff, the BL was still 10, but the AL was all screwed up. So this is a hard one. Okay, so I Hernandez has it right. So between the print sum and the print diff, AL was overwritten. That's right. So good one, Ember Wolf and OI Hernandez. So notice what happens in print sum procedure. I actually overwrite AL. And then I add to AL. And then I get a result in AL. That's a problem because print diff was expecting AL to remain unchanged. But when I did print sum, I actually changed AL. So print diff is getting the wrong AL. It's not the original AL. It's the AL that was wrecked by the print sum procedure. So without changing the way I do the calculations, what can I do to make it so that print sum does not blow up that register? A push and a pop. So Ember Wolf is right. So all I have to consider in my print sum procedure is that I want to use AL for some math, just temporarily. And I should think to myself when I write the print sum procedure, if I'm using a register temporarily, there might be another part of the program that's relying on that register to be left alone. So I will simply use the stack. I will push whatever A is starting out, and then I will pop it back to what it was when I'm done. That way I can use AL however I want without affecting other parts of the program that might need the A register to be intact. So Druid points out that I could use a different register like CL, but that becomes a huge management problem at a point. So if I'm constantly having to think, okay, which one was I using? Is it okay to use CL here? But what about BL and maybe DL? It's high performance and way easier to avoid mistakes by just saying, you know what? I'm about to rec AL. I'm going to use the stack to make sure that that doesn't affect other parts of the software. Problem solved. So problem solved. At least for that one. Now, of course, what happens if I say print max of BL and AL, and I have a procedure where I want to say print max between two values. That's a good question. So Druid asks in chat, what about pushing 16-bit versus pushing 32-bit registers? So you are allowed to push 16-bit registers, but the documentation suggests to you that you always push 32-bit registers, even though you don't always need 32 bits. So the stack is at its best performance when you push and pop 32-bit, even if you don't need it. You are allowed to push 16-bit and pop 16-bit. You are not allowed to push 8-bit and pop 8-bit. You are allowed to push and pop 16-bit, but the documentation recommends that you push and pop the whole 32 bits at a time for performance reasons. You get the best performance out of the stack if you work always in 32 bits. So that's what we'll do, is always push and pop 32 bits, even if it's not required. Yeah, so, and then Druid asked, so that's why I'm pushing all of EAX and not AX. And yeah, that's right. So that's my habit, is to always push and pop 32 bits, because I know that's the stack gets its best performance in 32-bit chunks. Okay, so is everyone following the print max? So we'll just, I'll do one more. So let's see here. I need a middleman. Doesn't really matter. So let's just say I'll use C. So I will say if CL greater than Y, then Y greater than CL. I'll say greater than or equal to on the first one. Actually, it's just an else, right? Max of X and Y is X. So I could use CL here, and that's fine. And that won't pollute my program. But let's just finish the thought on these procedures and get them kind of tightened up. So what I want you to start thinking about is how can I write a good, solid, robust procedure that doesn't pollute registers unnecessarily. Yes, you could. So Ember asks, could you just use the registers for the parameters? And you can use the registers for parameters if you want. I like parameters just, well, in programming generally, I like them because it makes it easy to, I don't have to understand other parts of the program if I'm using parameters. I don't have to go figure out which registers have the data that I need in which order. I can just have the parameters that represent those things for me. But it is true that you could use the registers in combination with the stack to avoid parameters entirely. Technically, by the way, that is what HLA is doing for you, actually, is using the stack to manage your parameters for you, interestingly enough. Okay, so what do I need to do in print diff so that I don't pollute registers unnecessarily? Push and pop EAX, good one. So Emerwolf's on top of that one. Yeah, so remember, OI Hernandez, you are not allowed to push and pop 8-bit registers at all. You won't be allowed to. The compiler will complain at you. You are allowed to push and pop the 16-bit parts, but you don't get the best stack performance if you push and pop 16 bits. So always, always, always just get in the habit right from the start of always going to the 32-bit part of the register and pushing and popping it. Okay, so so now Druid's question about the order that the procedures are implemented. So HLA follows the same rule basically as C++ does, which is you can implement the procedures in any order that you want to, but you can't call a procedure from anywhere before it has been declared. So for example, Druid, if I wanted to print sum from print diff, I'm not allowed to do that yet because print sum has not yet been declared and defined. So the order that you set up your procedures for now is not likely to matter, but you can't call a procedure before it's appeared in your code. Now, HLA does have a way of forward declaring things, which we will use eventually. But for now, it usually doesn't affect anything. Just be aware that the procedures can be defined in any order that you want, as long as there is no call to a procedure in your code before it has been declared. So if I needed to call print sum right here, then I would have to have declared print sum before that happened. So that's how that would work. I can call them in any order that I want to in the program. That part doesn't matter. I just can't call them before they have been declared and defined. But once they've been declared and defined, then I can call them in whatever order in the program itself that I want. So if I wanted to do, let me put that back. So I cannot do that. But I can. Where to go? I can call print diff before print sum. That's fine. And I can call print max before all those if I want to. So the calling order doesn't matter at all, as long as the call doesn't happen before the definition happens. That's all that matters, like C++. Okay, let's go ahead and tighten up print max. So even though I know that this particular setup is not polluting my current program, it is wise to take advantage of my knowledge to make sure that no matter what happens in the future of this particular piece of code, no matter what I do in the future, I'm going to make sure that this print max function does not accidentally pollute the rest of the program. So what do I need to do in print max to avoid polluting my program? even though I know I'm not doing it now, the day could come when I do, and I've forgotten about all this. Nice one, O.I. Hernandez. So yes, in this case, it's ECX, which picks up CL. And of course, we do 32 bits because we're told that that is the way to get the best performance out of the stack. But inside of ECX, of course, is CL. So that push achieves the goal. And then I pop it to restore it back. So now this procedure won't accidentally pollute other parts of the program. And sorry I'm running over by a few minutes, but I've got one more thing to show you real quick, which is a procedure like this. Let's just say get input. And I'll even document it. So let's say we have a procedure like this. This one is a little bit trickier. This is HLA syntax, by the way. It doesn't actually do anything other than document the return, more or less. But I wanted you to see it. So this get input, it is supposed to return a value. So what about this procedure? There you go. So O.I. Hernandez has seen it. This procedure, in fact, its stated purpose is to overwrite AX. So when you have a procedure that you want to return a value, we've done that with true-false values, for example. If a procedure returns a value, then the procedure has already kind of stated its intention to pollute a register. So since this procedure says, hey, I'm going to pollute AX with the user input, then we don't do push and pop here because that would defeat the purpose. If I push EAX here, knowing that the input is going to go into AX, and then pop EAX, that would defeat the purpose of the function because I'm supposed to get the input and leave it there, but I am popping and overwriting the input itself. So there are occasions when we won't use the stack in a procedure because we intend for the procedure to actually overwrite a register, and that's why we wrote it in the first place. So be mindful of that as well. We don't, in every last 100% of the situations, push and pop. In this case, because we want to leave AX overwritten. In these other procedures, we did not want to pollute AX, so we used the stack. Okay, so I need to quickly get to, I'm not going to show you my view change. I'm just going to go grab the lab code and let's see if there's anything scary looking in it. Okay, so this week's lab. So here's an example. This get number procedure, no use of the stack here. You don't want to use the stack here because you intend to overwrite AL. So do not use the stack in get number. Notice that go again does the same thing. It returns a value. So no use of the stack in go again because you want to overwrite a register when that procedure is done. Show graph is already setting up to suggest to you that you should be using the A and C register in here. And we can see why, because there's a loop that uses C, and there's a division that uses the A register. So show graph is pretty straightforward. The stack parts have already been done for you. Why A? Because we are using A for the division and A alone. Why C? Because we're using C for this for loop. So this procedure, show graph, is using the stack to make sure that the A and C registers don't get polluted when we don't intend to do that. Let's see the next procedure, total and average. So this one is make note of the registers that you use, whichever choices you make, and use the stack to preserve and restore them. Producing a sum is not hard, even of 4 numbers. That's just a series of adds, right? Computing the average is running a division by 4. These are 8-bit things, so the division will be 8-bit to 8-bit, which means AH and AL. All right, so that's that one. Minimum. So that's just a bunch of if-else kind of things. Which of these values is the biggest? Same thing, though. You're going to have to use a register middleman somewhere, which means that you will need to, or at least want to, use the stack to preserve and restore whatever registers you are overwriting. So every procedure here that you should be using the stack, it is pointed out to you that you should. Max will be the same. An if-else if kind of thing to figure out which of those 4 values is the biggest, which you will print out and then take note of what register or registers you end up using and use the stack to preserve and restore them. And then that's it. The main part is already completed for you. It's just waiting for you to do the procedures. Okay, that's pretty long. Let's call it a day. I will upload the week 8 code. It has the extra program at the bottom, and I will also upload these notes if anyone wants to see those notes. So thanks a bunch, as always, for the questions. This is a technical class, and there are some things that are unique and one-off, and you may never see them again in your life. So this is the place and the time to ask those kinds of questions. So they're always appreciated. Ask whatever you think you need to ask, and I will use my best judgment as I can to just to tell you sometimes that we don't want to go there, or when I can, I will endeavor to answer them, because they are, in fact, all relevant questions. So thanks as always. Have a good week. Piazza, Canvas Inbox, office hours if you have any questions. Please have a read at least through Project 2 at some point so that you know what's coming, and then you can start to watch our labs and see what you can pluck out of them for the second project. So everybody have a great day. See you next week.